Good.
Super. So let me just start by welcoming everybody to this ECT STAR workshop. So this is tackling the real-time challenge in strongly correlated systems and spectral properties from Euclidean path integrals. So on behalf of myself, but of course also Alexander and Anthony, it's really a great pleasure to welcome you to the workshop. So I'm going to say just a couple of organizational sort of logistics things, and then I'll hand over to Gert, who can do an official welcome. But we are really very happy to see you all, not in person, of course, which is a pity, but to see you at last at this workshop. So for many of you, this will be a continuation of a series of events, workshops that have taken place over the last couple of years. So the CERN workshop in 2019 and Amherst last year on a similar theme, and we've included some links to the web pages for those conferences, so you can have a look, and if you're interested, see what talks were there and some of the slides. So we're a little bit delayed, a year delay. We had planned for this workshop actually a year ago, but we're really very happy that everybody continues to be so interested and willing to participate. And I think it speaks to the problem that we're going to be discussing, that it is a continuing challenge and also, of course, of continuing interest across a range of physics topics that have brought us all here together for this workshop this week. I should say that if looking back at the CERN workshop and the Amherst workshop, so I was very happy to be a speaker at both of those workshops, but Alexander and Anthony were organizers of these on these different workshops, and so it's been a pleasure to join them in the organization of this installment here at ECT STAR. So just a couple of logistic things and organizational things. So of course, as you know, you can see the timetable on Indigo as usual. Please do remember to upload your slides also to the Indigo page. And that will also help, of course, others who may not be able to join the sessions, but of course, also in case of any technical problems, we can help out as well during the talks. The Zoom link and the password for this meeting are given here, just again for convenience. And a reminder, as you might have seen in the chat as well, to fill out the privacy agreement for recording of these talks, which will be recorded and then uploaded to YouTube with your permission. Okay, and we can provide further information on where to watch the recordings in the coming days. Okay, so maybe just a couple of words about the timetable. So if you've had a chance to look at the Indigo timetable, you'll see that we're alternating the morning and afternoon sessions. So starting, of course, this afternoon, continuing tomorrow morning, then Wednesday afternoon, Thursday morning, and finally finishing up on Friday afternoon. So what we have hoped that we can do in that sort of alternating arrangement is to accommodate colleagues in the US and in Asia, so that you're not always having to stay up very late or get up very early to be able to participate in listen to the talks and participate in the discussions. And we also had in mind that by now everybody is suffering from Zoom fatigue, and large blocks of talks are maybe not so constructive or so helpful for discussion sessions. And so we're hoping that we can have very lively and very collaborative discussions throughout this workshop using this timetable. So the emphasis, as I said, is really on discussions. You have some talks, which the invited talks, which we've hopefully arranged so that they set the scene for discussions then that we'll have in the workshop on the different days. There are some informal sessions. So for a start, we have virtual coffee sessions. So again, it's a pity we can't all gather around the coffee machine at ECT STAR, but instead the Zoom link will stay open during the coffee sessions, and you're very welcome to grab a coffee and just join in informal discussions during the coffee breaks. This afternoon, we have an informal discussion session at the end of our first day. And again, that's really just a chance for us to discuss some questions, to discuss the talks that we've heard, but without a particular focus or a moderator. And then on Tuesday and on Thursday, we've got some slightly more formal discussion sessions planned, where we'll be looking at the sort of broad picture in terms of applications. And here, Max Hansen has agreed to moderate, to chair that discussion session. And on Thursday, I think I've got it the right way around, Alexander will moderate a discussion on the various different methods that we will have heard about during the talks, and which we can discuss aspects of methods and strengths and weaknesses and all of those good things. So Alexander will help us with that later in the week. So of course, I should also, on behalf of Alexander and Anthony, myself, say thank you to our sponsors, ECT Star, of course, and for all of their help, in particular Barbara, who I think is still there, has been very helpful with all of the administrative aspect and setting up web pages and things like that. And also to the Strong 2020 grant, which is, again, providing support and in particular encouraging networking between researchers coming from different disciplines and different fields to discuss physics of common interest. Okay, so I think for me that's, yeah, so I'm just checking I had included everything. So from me in terms of logistics, that's everything that I wanted to say. I'm going to hand over to, well, our workshop participant, but also wearing his ECT Star director's hat, Geert, for maybe a few words of welcome to everybody. So let me stop sharing. And Geert, the floor is yours.
Thanks a lot, Sinead and all. Here we are. So Barbara will be there at all your talks and writing a paper at the end. No, that's a joke. So welcome everyone. So for those of you who don't know me, I'm Geert Aerts and I'm currently ECT Star director, and it's a pleasure to welcome you. So I just want to say a few things about ECT Star. For those of you who are not familiar with it, it was established in 1993, so quite a long time ago. And its goals are to be a center of the front line of research in theoretical nuclear physics, to promote contact between theory and experiment and also related areas of research. And then finally to train young researchers. And I'll talk about these a little bit more further down. And we're a member of NUPEC. It's very similar to experimental labs. And finally, the approach ECT Star takes, it's very much a community-driven bottom-up initiative. So the contributions from all of you are very welcome in terms of the scientific program and direction. And so this is a poster with the overview of 2021. It's also on the website, probably a little bit small to read. So we have continued the scientific program, as you know, with online workshops and training programs. This meeting is probably the last one, which is completely online, and the next one will be in hybrid mode, so that will be quite interesting. We invested some funding in the purchase of cameras in the seminar room, so we can give hopefully a proper hybrid experience, but obviously we haven't tested it yet because we haven't had the first workshop yet. I want to say two things about the training program. So these are the schools and the doctoral training program that take place every year. They're on topics which are related to nuclear physics or say slightly outside standard nuclear physics. Particularly this year, we had one on machine learning and another one on quantum technology. So these are interesting areas of research which have come up in the past few years and which now also make impact on nuclear physics. So this is an interesting area. And finally, of course, we also have a visitor program, which is currently on hold because there's only a few people working in the ECT Star in person at the moment. But hopefully this will resume, say, next year when things may go back to normal. Okay, we have a Twitter account. I know that some of you are on Twitter and already following the account like Alexander. But please join if you, and Sinead as well, actually. Yeah. But please join if you don't, if you haven't joined yet. Related areas, just a few words because it's very broad, and that is what makes the ECT STAR program even more interesting. Of course, it just some topics: astrophysics, cosmology, quantum matter physics, computational physics, ultra-cold atomic gases, but also quantum technology, quantum computing. And as I said, as reflected in the training program, these areas are quite new and upcoming and make an impact already in nuclear physics. So it's interesting to keep an eye out for opportunities in this field. The program at ECT STAR is determined by the scientific board, and current membership is given here. Marcella Grasso is the chair. And this is one example where the bottom-up approach is working. So membership of the board is based on suggestions from ECT STAR associates, and ECT STAR associates are everyone who has been participating in activities. So everyone who's joined this workshop becomes an associate by definition. There is a local research group as well. So there are 5 so-called senior researchers working in nuclear physics and computational physics. And then there are currently 10 postdocs working again in the same areas. So it's important to keep this in mind because typically as a visitor, you're familiar with ECT STAR as a place to hold workshops, but this local activity is obviously important for the local research environment. And one of our researchers recently won a fellowship to go to Jefferson Lab on a 6-month placement, and so this Francesco Celiberto, and 3 postdocs were awarded this fellowship, and Francesco is the only one not based in the US. So obviously we're very proud of this achievement, locally, so to speak. A few words about funding. So the FBK, the Bruno Kessler Foundation, provides the main support for the infrastructure. And then there's institutional support from the funding agencies, additional funding from Horizon 2020, like Strong 2020, and there are also individual projects like Marie Curie projects. And here's an overview of all the agencies. So these are the national agencies in the various countries. FBK, these are the current EU projects. ENSA has come to an end though. And then there's some additional German contributors as well. So if a question comes up in your local funding agency or your national funding agency, why do we pay for ECT STAR? Make sure to make it very clear that's important to contribute. So this workshop is supported by Strong 2020, and it would be very useful to acknowledge this in the publications that come out of this meeting. And so this sentence will be sent around to you by Barbara, to the organizers, to share. So please put this sentence in your acknowledgements. That's it. So for those of you who haven't been to ECT STAR, this is the building where you normally would be now, and you would have coffee down here in the basement. And I'm very much looking forward to welcoming you again in person at this particular place. Okay, so thanks a lot.
Thanks very much, Gert. That was great. Thank you. I know that you're under pressure, so I know you're going to run off now, but hopefully you will be able to join us during the week, since I know the topic is interesting as well for you. So hope to see you soon.
I hope so.
So thanks again. So just to say, the 3 of us, so Anthony, Alexander, and myself, put together some slides to set out what we see as the scope of the meeting and the challenges that we would like to, that we were interested in and that we hope to address during the meeting. So Anthony is going to present that for you. So I'll hand over to Anthony. So the floor is yours, Anthony.
Thank you. And so thanks everybody for the kind words to set up the workshops. Thanks to our sponsors once more for making this workshop possible. And as we already mentioned a minute ago, we really feel that this workshop is somehow in a line of a longer discussion, that has been started a few years ago with this string of workshops, and we kind of thought it would be a good idea to kind of summarize what we feel the insights have been that we have gathered in this time. And so to start you up and like to get really everybody ready for the workshop, we are going to just talk about the scope and challenge of those workshops. So one of the things that we really think is important, because it came up more and more and more, is that we really need to foster the exchange between fields and topics on this, because the inverse problem is an ubiquitous problem. It turns up in what's it called, geography, where the Backus-Gilbert method was actually first deployed, which is now seeing a huge usage, or a variant thereof, in our field, in particle physics and particular lattice QCD. And we really see this kind of cross correlation between different fields, because these inverse problems are so ubiquitous. So from high energy nuclear physics to condensed matter physics, there's something there. So we really want to foster this exchange, which is part of the aim of this workshop. We also need to understand a little bit better the range of phenomena, and for where real-time dynamics is really relevant and challenging and important. Can we reformulate problems in a way that the real-time property can be extracted from a static property? Is that possible? In some EFT languages, that is. So things that we are typically interested in are things like hadronic resonances, transport and momentum phenomena, in, for example, the quark-gluon plasma, or any other conductivity kind of phenomenon in the form of transport coefficients, where we then do the inverse problem, get the spectral function, read off the interesting physics that we're interested in. However, how do we approach this, and what is the right way? That is one of the things that we want to explore here through new conceptual technical ideas and advances, and to just gather them here in this workshop and discuss them. What do we believe are the comparative strengths and weaknesses of these different methods? And then a huge chunk of our discussion has always been, how do we estimate the systematics on our results? That will be a central aspect we hope to also touch on in the discussion sessions. So the scientific theme for this workshop somehow is bridging the gap. What are the numerical methods for inverse problems? Can we set up this interdisciplinary dialogue through the talks that we have here? What have been the advances in the extraction of spectral functions in nuclear and condensed matter physics? How did they manage these advances? How did they get their results? And is there something that you can take home for your own research? This kind of ties in also with advances in finite volume spectral analysis, which has had a huge impact in vacuum spectroscopy and lattice QCD, where you set up essentially a variational problem and solve it and resolve the finite volume spectrum state by state, and therefore you kind of circumvent having to do this inverse problem. That is something we also want to touch upon here, and to draw the connection to what we typically do when we solve the inverse problem, which is this third point, connecting the spectral function reconstruction and specific finite volume approaches. There is a new thought here, which we will hear all about, I believe, on Thursday, about the role of smearing, for example, and how the finite volume and infinite volume spectral functions can be connected. This also goes, of course, throughout these discussions, we will be talking about the systematics and complementarities of methods. And this is also, we hope, part of the discussions and part of the comments. We really want to ask you to be active in participating and pointing out, look, like in my method, this is how this works, and I'm confused about what you're saying right here. We really want to understand these different methods for progress. Which goes also towards novel techniques. There have been new methods out there that perhaps aren't on everybody's radar, but that might improve access to real-time properties. One thing that is somehow new is that we are in an era of very high precision data. And that opens up new avenues, some that, like when I did my PhD on this topic, perhaps were completely unthinkable. That the data quality was just not there. How do we react to this situation is also an interesting question, and one specific thing that came out of this is that suddenly machine learning methods have become interesting because the data is there to actually train these neural nets, which is something that was previously just not the case. And then you ask yourself, okay, deep machine learning, deep learning, what is their benefit? How do they actually act? How do you work with them? And what is the practical experience from people who have worked in this field for a longer time? So there is also some PDF expert talks in this workshop to give you an idea, because they are also, we are faced with an inverse problem. However, it is typically attacked or commonly attacked nowadays through machine learning. And to give you an idea of this, I've been talking about inverse problems, but not everybody is fully aware of what we're talking about. Some are very junior colleagues and have not been able to participate in this this discussion over the last few years. And the main thing is somehow this diagram, just in a picturesque overview kind of way, which is we have the thing that we want, which is typically this row of omega at the bottom. And the way to access this is either through Euclidean correlation functions or through Minkowski correlation functions, so Minkowskian time, so imaginary, so real-time data or imaginary time data. Typically, many of us in this workshop are coming from a lattice QCD background, so we will always be faced with having Euclidean correlation functions. So we will always be attempting to do this thing from the left here down to the row, which is an inverse Laplace transform, which is ill-posed, which I will talk about in a second. Of course, if you had an alternative approach with emerging quantum technologies coming up, like what Geert mentioned a second ago, or in the small systems which are possible in condensed matter context, you might not have this problem. You might actually be faced with a Minkowski correlation function. However, even there, nothing is ever free. There's no free lunch. So also there, it would be interesting to understand better how this Fourier transformation is actually done in real life and what the relation in practice is when you do this analytic continuation from the left to the right and vice versa. So those are kind of overview questions that stand behind the theme of this workshop, and I think it will be interesting to learn a little bit more. One thing that we are always struggling with is an effect of information loss in a way, because here I wrote it as an inverse Laplace transform. However, the kernel is somehow generic. It kind of depends on the system that you're looking at. If you're looking at a vacuum zero temperature quantity, in particular in lattice QCD hadronic spectral functions, they will always have this e to the minus omega t kernel function, so precisely this inverse Laplace transform. However, when you go to non-zero temperature, when you take into account the periodicity of the time direction on the lattice, then you will have this cosh of a sinh different kind of kernel function, or even if you do a parton distribution function, it looks completely different. And these kernel functions are just given on the right here to give you an idea of how they look. However, they also show you immediately that there's always this exponential decay of the eigenvalues, that there's always a heavy suppression of typically the long distance physics that we're interested in through the convolution with the kernel, so that it always makes it very difficult to actually get at the information and the physics that you're interested in. Let's say you are interested in the rho peak, for example, and you wanted to do this with a spectral reconstruction. That is a low energy, large distance quantity where we typically have noise problems where the data quality is not there. And then this convolution with the exponential makes it even harder because it suppresses all of the contributions of the physics I'm interested in at short distances. So the kernel, how is that entering? Is there any tricks that we can do? And I know that there are some of the speakers here that we've invited who have successfully applied some tricks here to enhance the information content of the physics we're interested in at short distances. Nevertheless, we should be a little bit careful with our expectations. So this is a slide that we showed at the Amherst workshop, actually in a joint discussion session that Max and I led, which I think is very instructive and is something to keep in mind, because in the end we are attempting the solution of an ill-posed problem. Then you ask yourself, okay, what is an ill-solved problem and ill-posed problem? And this goes back after some Googling. This goes back to Jack Hadamard, who established 3 conditions for a well-posed problem, which is that first of all, that the solution to this problem exists. Second of all, that it is unique. And third of all, that it is stable, that you can apply, that the solution's behavior changes in some predictable way, depending on the initial conditions. This is in particular interesting also for Bayesian methods. So the problems that we typically consider, the existence of the solution is not a problem. We know that the solution exists. The problem is always the uniqueness and the stability. And these are also aspects, I think, which throughout the workshop, we will really see in many, many different contexts with many different backgrounds. All methods somehow face these 2 problems, which leads us to say, look, this is a problem due to the discrete sampling and finite precision, something that is not something we can just solve. So this is something that really has to set your expectations. Your result will always depend somehow on the discreteness of your data and the precision of your data. And how to quantify what that means then for our predictions is part of this workshop to get to some statement there. The community overview is then, I thought this quote was really nice that Sinead showed also at the Amherst workshop, is an open question. What is an open question? That is a matter that is not yet decided or is unable to be decided. And right now, we don't quite know. Is it not yet decided or is it unable to be decided? That is something to work on. And observations that were written down back then, and I repeat here, are that observation 1 is that there have been common themes emerging throughout the community. And this is also something we built the program to reflect when we selected the speakers, that you will see this common theme and the common questions, which are uncertainty, quantification, robustness of the results. How do we add extra information? Observation 2 would be that the data has fundamentally changed in the last few years, the point that I mentioned a second ago, that previously, if you think of the spectral reconstructions of the late 90s and early 2000s, that the situation there was very much lacking in data, also lacking in computing power. If you think of the usage of the MEM, for example, nowadays, Alexander actually has a nice proceedings where he mentions that you can just Monte Carlo that. You are not limited by computational power in that sense anymore, that you have to go the MEM route necessarily. That is very interesting, and it also opens this machine learning direction. Then domain knowledge, something that we kind of have an ear on, depending on which methods you typically work on, which is what is the role of the extra information? How do you quantify the effect and impact of extra information that you give into the problem, into the solution of the problem? This idea being that, okay, you have an ill-posed problem, there's not enough information in the data itself to solve it, so you add something on top. And I think one of the main systematics, especially in Bayesian methods, has been, the main problems has been to estimate the systematics that originate from this and to do this in a controllable way. I think that is something important to understand. How does this prior information and extra information that we put affect our outcome and the trustability of our result? Because of course I could say, well, I do a fit, I have a model, and as long as the model is correct, then that's my solution. However, that is quite far away from what most of us practitioners in numerical ab initio theory do. Typically, we want to say this is an ab initio result with as little tampering with from my side as possible. And this is then an important aspect, because those that we present our results to will typically not see this. They will think that this has the same ab initio character as before. Is there a comment? No. And this leads to observation 3, that some communities have made progress in the category of understanding complementary observables, but there have not been any concerted efforts in this direction, which is like an impetus we would like to give. Throughout the workshop, we will see quite a large number of methods being showcased. Most of you who have been around for a while will have some working knowledge of all of them. Just putting them into 4 broad categories. We have the frequentist type models, which are what we would call just fits. You fit a model to your data. There you typically have a problem that the parameters of your model are under constrained. The oppositeness of the problem emerges as if you were to plot a chi-square kind of landscape. You would not see a global minimum, but you would see large regions of degenerate minima that prohibit you from drawing any robust conclusions. This was, I think, very nicely shown in the context of the thermal production rates by the Mainz group. Then you have the Bayesian methods, the way you do the maximum entropy methods or the BOR method or similar variants thereof, where Alexander is a real expert, and we will hear also some other results also from other groups, for example, FastSum, how they deploy these methods to their advantage. The question there is always this question that we had a slide before: what is the impact of the prior information here? What is the impact of the method itself? Some of you will remember that there was a bit of a discussion between Alexander and Yuki, I forgot his name, from Japan. The discussion about the validity of the BR zone, yes or no, and the validity of the MEM. There we had a little bit of a masterclass series, and I think that was already also very interesting, giving us a view into the inner workings of these methods. And I think we can discuss this a little bit closer also in the methods section. Then the new thing, which I think is rather exciting, are these linear methods. The huge benefit, of course, being that they're linear. These are the Backus-Gilbert method and the Hansen-Tantalo-Lupo method, from which we will hear quite a number of talks, I believe, in how to perform the spectral reconstruction. Then, when your goal is to, instead of getting the finite volume spectral function, is to get a smeared version thereof and then to control the smearing. I think that is very exciting. Finally, we have the machine learning and neural networks, where we also have the classical and the quantum versions of those. Quantum machine learning being a very recent development, a very interesting development, and we will hear about those things on Friday. Of course, each method has its own inherent and problem-dependent pros and cons. And this leads us to observation number 4, which is that there's unlikely a single best solution. Like, there will not be a generic throw this method at any given problem, and you will get a trustable, great result. It will always be an engineered, adapted to the system, to the question at hand solution. So it is important to quantify where which method performs best and what to expect of the performance of a given method that you're looking for. It is not enough to simply observe that results agree. That is clear. It has to be properly quantified. So that is then where we go to what we hope to discuss, which is proving and extending methods. What are new ideas, especially what I mentioned a second ago, this rapid progress in understanding the finite volume spectrum at zero temperature. Can messages from there be treated? Can we learn something from there? Can the finite volume be used as a tool? What is the role and the use of smearing in these Backus-Gilbert type and Hansen-Tantalo-Lupo kind of type methods? What about promoting the inverse problem to a variational problem as well? Is there a benefit in that? This is something that we discussed on and off throughout the last workshops. And then, of course, can we find EFT formulations to our problems that simplify the access to the physics that we're actually interested in? This will be often not possible, but where it is possible, avoiding the inverse problem is the best solution to the inverse problem. This gives us to our challenges. Can we actually, it might not be possible, can we actually articulate the relevant systematics? Can we quantify them in a good way that is somehow standardized? Is there a hierarchy of some systematics that we can dominate? This would give us a path how to improve our results. Is that clear? And that is a method-dependent statement, and for some methods, this might not exist. How do we compare results from different methods? That is kind of the same question. And also, if we communicate to the larger community outside of our expert field, how do we do so in a good way that the people know what to trust and what not? And I hope so. Like, that was a lot of chit chat from my side, just like trying to set this stage, trying to get you guys to think and remember what we talked about over the last few years. It has been quite a long time, and with a huge pandemic in beneath, to me, it feels like it's decades ago. To get everybody back up to speed. And with that, I think the three of us, we really wish you and us a great and fruitful week here at the virtual ECT Star. In the future, we'll be back in the villa, of course. And one thing I'd like to point out here actually is that one of the things I really marvel at that has come from the pandemic is the miracle of virtuality, that we can have these workshops with all of these people there without them having to get on an airplane. So I think that we have almost equal participating institutes from America, Asia, and Europe at an ECT Star workshop, I think is very unique. That we have so many participating institutes in America and in Asia and in Europe. I think that is really great, and we really wish that you have a great time here and can take a lot away from it. And thank you for joining us for this. And I think with that, I will stop the share and hand back to Sinead for next announcements.
Yep. Thanks very much, Anthony. So I hope that was helpful. It was certainly really very nice and very clear, Anthony, and I think reflected a lot of the thinking that and conversations that the three of us have had, starting back in CERN, but then continuing through the Amherst meeting last year, and then prompting us to organize this workshop and hopefully give you a glimpse into the topics that we think are interesting and relevant, and hopefully that you do as well. So we have on the timetable, we're taking a break for coffee, a virtual coffee break. The Zoom link will stay open, and we can chat about what Anthony has discussed and the questions that he has raised. And we will reconvene formally at 2:30 Italian time for the first invited speaker for this conference, is Martha Constantino, who's going to talk about the inverse problem in hadron structure from lattice QC. For the formal coffee break, Alexander, you haven't had a chance to say anything. I'm not sure, did we forget anything, or is there something that you'd like to say before we break for coffee?
No, I think this was a really nice introduction by Anthony, and I really encourage everyone to use the discussion sessions. This is thought to be an informal workshop, an informal atmosphere, and I really hope that we can maybe get some bit more heated discussions than what one would have at a larger conference, to really spell out what you as practitioners think. What is the challenges? What are the directions where we should go? What are the directions that you think will not pay off in the future? And so I'm very much looking forward to our informal discussion sessions, to be a bit more to the moderated discussion session on Tuesday, tomorrow, by Max, on somehow the application side of the inverse problems, and I hope to be able to welcome a lot of you for the discussion session on Thursday on methods, where I hope that we can really somehow challenge each other's experiences with different methods, and which of those play out their strengths and weaknesses. And with that, I really am just looking forward to the talks and discussions that are coming up.